Hello everybody. In this video we're going to talk about confidence intervals for the population mean in the situation where the population standard deviation is not known. All right, in the last few videos we looked at the situation where the population standard deviation was a known quantity. Of course, in reality, you probably don't know that, right? We don't have the population parameters at hand. We are trying to approximate these. Right? We don't have access to the entire population. We can't go out and measure everybody. So we wouldn't know in general what the population standard deviation was. There are situations where you might have that information, but in general we don't. And so we're going to look at what to do in that scenario if we don't know what the population standard deviation is. So we're going to start by looking at a situation where we do know the population standard deviation, so we're going to review the process from the last video, and then we're going to look at the case where we don't, and we'll compare those two situations. Okay, so let's go take a look here. This is the example from the previous video that we looked at. Exam scores. It says, suppose scores on exams in statistics at a college are normally distributed with an unknown population mean and a population standard deviation of 9 points. A random sample of 40 scores is taken and gives a sample mean of 74. Find a 95% confidence interval estimate for the population mean. Okay, so what do? Well, we make note of these facts here. So the standard deviation is 9. All right, so I'm going to write that down. That's the population standard deviation. It's known to us. The sample consisted of 40 scores, so we have n equals 40. That's our sample size. We've computed a sample mean, x bar equals 74. Okay, we got that. And we want to find a 95% confidence interval. So what drives this whole process is the central limit theorem. Okay, so we need to know that we can use the central limit theorem. We can use the central limit theorem if our sample size is big enough or if we know that the original distribution was normal. We know both in this situation. We know that the original distribution was normally distributed and our sample size is quite large. So we actually have both of those conditions satisfied. So we are good to go. Okay, so how do we proceed? Well, we need to find the critical z-score corresponding to a 95% confidence interval. You might remember from the last video that was what that was. Let's go through the process of computing it again so that we can compare this to the situation that we'll have in the next example. Okay, so how will we compute this? Well, we will go to our calculator here, our statistics calculator, and go find this out. All right, so we'll go get our normal distribution calculator. And I want to find in the normal distribution the z-value, the z-score, that bounds 95% of the data. So I want to have 95% of the data between plus or minus that z-value. So I'm going to put 95 here, 0.95. Compute it out, and we see that that critical z-score is 1.96. But looking at the picture here, you can see this is negative 1.96 over here. This is positive 1.96 over here. Between them, the red shaded region is exactly 95% of the area. That corresponds to a 95% confidence interval. Okay, so what did we find out? We found out our z-star value is 1.96. And what does that allow us to do? That allows us to compute our margin of error for our confidence interval. Our margin of error is z-star times sigma over the square root of the sample size, n. And so let's go ahead and compute this. This is our z-star was 1.96. We're multiplying that by 9 divided by the square root of 40. And when you do this in this situation, you get about 2.79. Okay, that's our margin of error. That's how far we can move away from our sample mean to make our confidence interval. So I'm going to add and subtract this value from our sample mean. So let's subtract it. see what we get. If I subtract this value from our sample mean, so I'm taking 74 minus 2.79, I get 71.21. And if I add this value to our sample mean, I get 76.79. Okay, so what do we conclude? Well, here's our confidence interval. We conclude the following. With 95% confidence, we believe that the mean exam score among all exam scores at the college is between 71.21 and 76.79. That's our confidence interval and stated with our level of confidence. Okay, this is what we did in the last video. Okay, so what we're going to look at next is an example where we don't know the population standard deviation. So let's take a look here. Problem looks almost identical, all right? Exam scores are normally distributed with an unknown population mean. A random sample of 40 scores is taken and gives a sample mean of 74 and a sample standard deviation of 9 points. Find a 95% confidence interval estimate for the population mean exam score. Look what's different between this example and the last one. In the last example, well, let's write down the parameters we have and just take a look. All right, so let's just go through these one by one. A random sample of 40 scores, so we have n equals 40. Okay, sample mean of 74. Sample standard deviation of 9. That's the sample standard deviation, and that's the difference right there. Look at that. Last time we had the population standard deviation. This time we don't have that. But since we took a sample, we can compute the sample standard deviation. Okay, so now the S represents the standard deviation from our sample. And now we want to find a 95% confidence interval. Well, can we proceed as we did before? Well, the answer to that is no. We have to be a little bit more careful here. Let me explain why. Okay, so what we did before was based on the idea that we looked at the z-scores and we found the critical z-score, that z-star value. That was the value that bounded 95% of the data, right? So z-star was here, minus z-star was here, and 95% of the data was in between. What did we use here? What distribution? We used the normal distribution. And we were allowed to use that from the central limit theorem. Right? It told us that the sample means were normally distributed. So these are the distribution of z-scores here. Okay? What are z-scores? The z-score is computed as follows. You take the statistic that you're measuring, in this case it was the sample mean, you subtract the true mean, right? And you divide by the standard deviation of whatever it is you're measuring. In this case, we're dividing by the standard deviation of the sample means. We didn't do this computation in the last example, but this is really the machinery driving what we were talking about. Now, what is the standard deviation of the sample means? Well, that is, from the central limit theorem, it tells us that's the standard deviation divided by the square root of the sample size. That's the standard deviation of the original distribution, right? Divided by the square root of the sample size. Okay, so that's how we get our z-score, and we know that that follows a normal distribution. Well, look at what's different in our situation this time. We don't have this value. We don't have sigma. Instead of the population standard deviation, we have the sample standard deviation. So instead of this formula, what we're going to be using is this formula. We're going to replace the population standard deviation with the next best thing we do have, the sample standard deviation. All right? Now, is that a z-score? Well, the answer is no. The z-score is defined in terms of the population standard deviation here. So this is not a z-score. What we call this is a t-score. It's something else. Let's give it the name t. Okay? So now we have to think about how these t's are distributed. Okay? So let's imagine the distribution. Turns out it's going to be some distribution. It turns out it is bell-shaped. It looks almost normal, but it's not exactly normal. This is a t distribution. But we want to proceed the same way, all right? So it's slightly different than a normal distribution, right? It's not normal. And it's actually the t distribution with n-1 degrees of freedom. You see, this is a statement about the type of t distribution. It turns out that there's different types of t distributions depending on the value of n, all right? And so what you do is you subtract 1 from n, and that determines the degrees of freedom, and that determines which t distribution you're looking at. And we'll see more about this in detail a little bit later. If you find that a little confusing, we'll see how to deal with that a little bit later. But the main point is we have some bell-shaped curve, and we want to find, just as before, which values bound 95% of the data according to that distribution. Well, it'll be between two values here. We call this t star and this minus t star. And so we're going to be after what this value is. And once we find that value, we're going to do exactly what we did before. We're going to write our margin of error. It's going to be the t star times this value here, s over root n. Compare that to what we had up here. In this picture, we used a margin of error equal to z star times sigma over root n. So now instead, we're using t star times s over root n. But now everything else proceeds the same way. Okay, so let's go back to our specific example here and work all this out. Let's see how this all plays out. All right, so this is what we've recorded. All right, we've got our sample size, our sample mean, sample standard deviation. Now we need to find t star. Okay, so let's go to it. What we're going to do is we're going to go to our probability calculator. Okay, this is not a normal distribution, so get rid of that. Let's load up our t distribution. Here it is. And I'm going to choose I want to find the t star value that bounds 95% of the data between, right? So I'm going to hit between here. I want the degrees of freedom. Notice they have a df here, degrees of freedom. That'll determine which t distribution we're looking at. Now, what was our sample size? Our sample size was 40. And remember, the degrees of freedom is n minus 1. So 40 minus 1 is 39. Okay, so that's the value that I'm going to plug in here, 39. And I want to bound 95% of the area, so I put 0.95. Just like in the normal distribution, my value pops out right here. It's 2.02. All right, so make note of that, 2.02. And now we proceed just like we did in the last example, right? The margin of error is given by 2.0, let me write this down, t star times s over root n. So that's 2.02 times 9 divided by the square root of 40. Okay, and that is approximately, if you compute that out, you get about 2.87. I'm rounding, so I'm going to put approximately equal to here. Okay, so now we compute our confidence interval endpoints. So I'm going to take x minus the margin of error I'm going to take x bar, sorry, it's x bar plus the margin of error. Okay. So what's x bar? It's 74 minus 2.87, and that is 71.13. And I'm going to take 74 plus 2.87. That is 76.87. Those are the endpoints of my confidence interval. And so I can write my final statement. With 95% confidence, we believe the mean exam score among all exam scores at the college is between 71.13 and 76.87. All right, so that's our conclusion. Now let's compare this to the result that we had before. All right, the result that we had before when sigma was known, right, was this. What we did here is what we did, this was the case where sigma is unknown. Okay. Which confidence interval is bigger? Well, you'll notice that this value is a little bit less than this value. This value is a little bit more than this value. This is a bigger confidence interval. We are being less precise. Why are we being less precise? Because we don't know the population standard deviation. We're using the sample standard deviation instead. We're using information that's a little bit sloppier. So we should expect less precision in our answer, and that's exactly what we see here. Okay, so the last thing I want to point out in this video is a little bit of information about the t-distribution. It's a little bit of a fun fact. The t-distribution was discovered by a fella by the name of William Seeley Gossett, all right? And he published under the name student. So he didn't publish under his own name, and he named this the t-distribution. So oftentimes you'll hear this called the student t-distribution. Okay, why did he publish under the name student? Why didn't he publish under his own name? Well, he was working for the Guinness Brewing Company. They brew beer. They still do to this day. And that company was using Gossett to do some research to help improve company profits. Right? He was employed for that purpose. But the company had a policy where they didn't want their employees to publish under their own names. Otherwise, the competing companies might understand, you know, what the Guinness Brewing Company, with some of the advanced methods that they were using. They didn't want those other companies to know about this. So they required their employees to publish under a pseudonym. All right, so William Gossett was not allowed to publish under his own name, so instead he just published under the name student. And so this is known as the student t-distribution, but it really should be called the Gossett distribution. So that's just a little fact about where this distribution came from and who came up with it. All right, so that's it for this video. Confidence intervals where the population standard deviation is unknown and the student t-distribution.